we were introducing this idea of mechanics as a whole topic, right? And we said the big difference between extension 1, motion, and extension 2, motion was, what's the big difference? Mass. Very good. So when you take these two key ideas, which we have done to death into an extension 1, right? And when you add mass to them, velocity and mass together, we gave it the name momentum. That's right. Okay? And its unit was kilogram meters per second. Yes? Because it's a velocity, meters per second, plus mass, kilogram meters per second. Okay? And then we said, well, if you do the same thing with acceleration, you bring mass into the equation, what do we call it? Force. Thank you. Right? So you got acceleration and mass considered together, that's a force, right? Now, just like this was kilogram meters per second, this was kilogram meters per second squared. But we decided that was such a mouthful, right? We invented a whole new unit for it. Units, right? Now, it's more than just new fancy names and new units, right? They're actually, you know, it's not just I'm figuratively and conceptually bringing mass in. I'm literally taking velocity and multiplying it by mass. That's why it's kilogram meters per second. And I'm literally taking acceleration and multiplying it by mass. Okay. So we looked at a quick example. Let's look at another one here. Okay. So typical setup. Here is the mass of an object, 2 kilos. Here's an expression for the force that's acting on that object in relation to its displacement. Okay, so we looked at this under extension 1 motion before. This is no big deal. This makes sense. We know that sometimes, depending on where something is, different forces are acting on it. Okay, so far so good. But now I'm going to pose a slightly different question to you, right? How am I going to find velocity as a function of displacement instead of force as a function of displacement? That's what this is, right? So I can see I've got a force equation here, right? I've got a mass and I want a velocity, right? So I'm going to begin with this. We start with this a lot, right? F equals ma. And now we can start to fill in, right? Okay, what have I got? I've got 6 minus 4x over here, right? And then I've got 2a, so rewriting. Okay, so suggestions. At this point, what should you do? Remember, we've got all these millions of ways of writing acceleration, and we choose the way that directs us best toward what we're trying to get, right? So I'm trying to go from A to V. So, suggestions? How would you choose? D, which way? Which way? You could go V, dV on dx. Now I believe, did we do this last time? Did we do this way last time? Yeah, we did. There's another way, right? There's another way to do this, and you will see shortly it's actually a better way. What was the other alternative? It's very similar to this one. It's d on dx of half v squared, right? You can see the clear relationship there. So just to shake it up a little bit, let's go with this. Let's see what happens. Let me put that in here. What was your immediate next line? What did you do? You integrated. No problems, okay? We can integrate. Half v squared equals 3x minus x squared. Okay, so far so good. Now what? Plus a constant. Okay, now what? So you want to evaluate the constant, do you? Is that what you want to do? Yes? Okay. So you take these. I'll just get another color so I don't mix this up with everything else. You say, when x equal to 1, v is equal to 2. So what will you get on the left-hand side? A half times 2 squared. Which is 2. Here, you'll get 3 minus 1 plus c. Yes? So what's c equal to? Okay, so if you forgot to put on the constant of integration, lucky you. Doesn't matter in this case, okay? So far we have this. Now what? Yeah? So now what? V equals plus or minus. So now what? Say it again a bit louder. Don't have to be afraid because everyone else in the room has said the same thing. Just say it again. V must be positive. Now, why do you say, like all 15 of you that I've already checked, why do you say V must be positive? You look at this condition. That's what you've done, right? You looked at this condition. Now, that is not a bad way to go. It's not a bad way to go. In most circumstances, it'd be fine. And you'd say, therefore, positive case only. But there's something you're missing. There's something you're missing. Now, before I tell you what's missing, let me just remind you, right? What makes trials, and by extension, you know, the actual HSC, difficult, is that rather than the tests you've been having so far, which is like, oh, I know it's these topics, so I know what I'm looking for. And then I know it's these topics, so I know what I'm looking for, right? Final HSC, they're just like, here's a question. It could be anything, right? So you have to rack your brains to think through, what do I know that I'm going to need to bring to bear on this question, right? So you're all in mechanics mode, right? You're like, okay, this is all good so far, but there's something that you know in here that will help you answer this question. And in fact, not say that, because it's not true. It is both. That's right. This is the final answer, but the question is why? Now, admittedly, right, oh, it's a force. I'm not used to thinking about that. But a force is primarily about acceleration, right? So if I rewrote it in a form that you're more familiar with, x double dot equals that, right? It's still maybe not quite perfectly obvious to you. What do I need to change to make it super obvious? Say it again. Well, yeah, okay. I'm just going to think about, I'm not going to worry about units right now, so the number will be there. But what's the condition that actually makes this thing special, right? Well, it's in this form, isn't it? How do I do this? I suppose I should put a -4 out the front. And that would make this, let's see, I will make an x minus, what, 3 on 2? 3 on 2? What's that? That's minus n squared, x minus x naught. This is simple harmonic motion, right? So in simple harmonic motion, of course it can go both ways, depending on which side of the center of motion that you are, right? Namely there, I guess, okay? So it's done. We forget to look for those kinds of things because there was no big flashing sign saying simple harmonic motion, right? But that's why we labored this point and said, there's ways to know that it's simple harmonic motion other than this, right? You push the center of motion somewhere else and you'll get this kind of situation, okay? Now, before we finish, some of you were suggesting before that instead of using this, we should use this, okay? Now, yesterday, I introduced to you a different way of doing this, of not having to evaluate a constant, not having an indefinite integral down there. How did we do it? What was the alternative? How would you rework this? How would you rework it? So we're going to integrate both sides with respect to different things, yes? So I'm going to have v dv over here, 3 minus 2x dx over here. Okay? Now when you slap the integrals on this, because this is with respect to v, I want v boundaries, right? Now I've got one, namely this guy, right? So I should have a 2 there, okay? Over here, on the next boundary, and I also have 1, right? Actually, it's 1. Now hold on a second. Now I've got 2 spots. What do I put in there? The answer is, well, I don't know what they are. That's kind of the point. I want v as a function of x. Right? So my dummy variable is in fact going to be the variable. Right? So let's go ahead. Let's do it, right? Integrate, what do I get? Half v squared. No surprises there. Okay. Between 2 and v. Okay, what do I get over here? This is what I had before, right? From 1 to x. No constants of integration inside, right? What happens? Half v squared minus 3x minus x squared minus 3 minus 1, which is 3 minus 1, right? Yeah. Which is minus 2. Okay. So this constant and this constant are going to disappear. Of course they should. They should. You knew they would, right? So a half v squared equals 3x minus x squared, just like you got before. It's the same thing, right? You're gonna dot dot dot. You're gonna get to here. Okay. So you've got, well, it's roughly the same amount of working, but I quite like this way of ignoring the fact that you don't need to worry about a constant integration. Okay.